Good morning. So early start, and I'll just kick it off. So first of all, I want to say it's a pleasure to be here and collaborating with APAN for this conference. And today we have prepared two separate talks, but they are quite connected. So of course, we know AI is here, right? So Paresh will discuss with us a little bit on what does it mean for our networks, right? And then if we're investing in those networks, building them up, making some important researching, gathering data, transmitting it, then we want to protect this environment, right? So Kashimura-san in the second session will talk a little bit about what are the countermeasures. How can we protect this investment? How can we protect this data, right, and the network? So without further ado, and since we are a short group, I will encourage that we, make it interactive. If you have questions, don't be shy, and I'll just pass by with the microphone. All right? So Paresh, please.
Right. Thank you. Is this on? Right. You can hear me? Awesome. Thanks for the kind introduction, and a very good morning to all of you. Firstly, thank you for coming. It's an early morning start, and it's pretty cold, so really appreciate you joining the session this morning. So as Philippe said, what we'd like to do, at least I'd like to start off with over the next 40 minutes or so, is to consider some of the different elements of AI, but AI as it relates to networking, right? So most of us here, I imagine, are networking folks, and we'd like to understand what that means for us from a number of different perspectives. So the way I've constructed this session is actually split into 4 parts. So it's on
this one. I think a little bit louder.
Is this better? Right. So that was just my voice. All right. I think I've got natural projection. I didn't turn it on. Right. And here I am telling you about AI when I can't turn on a mic. So take everything I say with a pinch of salt. All right. So the agenda for today is firstly to look at AI in the market. I'm not going to spend too much time on this. I think everyone knows what is going on. We'll look at some of the workings of AI, right? And particularly from the perspective of what that means from the network side of things. We'll look at AI and networking in a bit more detail. And then, this is a Nokia session, so we can't let you go home without telling you a little bit about what we do in this space. In fact, we do a lot in this space. So the idea is to give you some of an overview of what that is. So AI in the market, I think it's pretty safe to say that we in the era of AI already, right? And, talking to my Bell Labs colleagues, they tell me that AI has been in the works for about 50 years, right? So it's not new. It's just that we've reached a point in time where many things have come together. Computational capabilities, the deep neural network learning processes, transformers, and applications that actually make sense to the average user out there, right? So as you saw with ChatGPT, when I was preparing for this, I went back and looked at when ChatGPT 3 came out, or GPT-3 came out, November of 2022. It's not that long, right? But it seems like it's been there forever. And it's partly, the amount of development that's happened since then as well. It rapidly raised to 100 million subscribers in 2 months, right? And just to put it into perspective, Twitter took 64 months, almost 5 years. Okay, they have different appeals, right? Those 2 applications. But just to show that, this is a market that's hungry for AI. The number of enterprise applications is growing. And if you follow the money, right, you see that there's a lot of money being injected into AI. When the new U.S. president was inaugurated, you heard about the massive, almost obscene amounts of money being thrown into AI. We expect that the market for AI will be a couple of trillion by 2030, and that's probably an understatement, right? But this is based on current projections. NVIDIA, we know, has become a multi-trillion-dollar company. I wanted to put a figure there, but that number changes every day, right? It's swinging so hard. So when I checked last night, it was 2.7 trillion. It's probably gone down a little bit more overnight as well. But it's really, it's really making waves in the market. But Even if you look at these applications that AI has enabled, you could say we are just scratching the surface when it comes to AI, right? And the way sort of we put it here is that we're kind of in a pre-Cambrian kind of era of AI applications. We've seen a lot of traction around language processing, natural language processing, and generative AI, right? And what it's done with things like ChatGPT, the creational or the generative aspect of it for not just text, but audio and video is getting applications out there. It's getting abused as well. So there's a lot of work that needs to be done on the regulatory side of things to rein in AI and put boundaries around what we can and cannot do with it. And it's been used in the computing world for code generation for lazy coders like myself, things like refactoring and so on. And many other applications, right? I mean, does anyone here do photography? Anyone do photography? Yeah. So if you use Adobe Lightroom, which I use extensively, I'm amazed at what you can do with AI, right? One of the things that I've been using quite extensively with Lightroom is the denoise feature that uses AI. So I've got some images that I shot at an ISO of 25,600, right? So if you know anything about photography, you'll know that that's a very noisy image. But what it can do with that is absolutely astounding. So many different applications out there, and we're just beginning this, right? Now, from the network perspective, one of the things that we are always, I guess, cognizant of is the impact of new technologies and applications on the actual network traffic. So Bell Labs Consulting, which is a part of Nokia, did a bit of analysis of this, right? They did a study to see how AI would impact traffic. So what you see on the graph is the global consumer traffic in exabytes per month, right? So it's once again a very, very large quantity. And I'll quickly go through this for you. So the dark blue curve that you see here is the non-AI traffic. So traffic that would just go up with or without AI, right? And we expect that it's a CAGR of around 16%. So it's going to continue along its merry way. And then there's the traffic that's being generated as a result of AI. And we split it into two things. One is traffic that is directly generated by AI applications like ChatGPT or any of your image generation or video generation software. So direct use of an AI tool. So we see that that's going to grow at a CAGR of 53%, right? Admittedly, from a very small base. But the more interesting one is the impact that AI will have on existing applications. And we're seeing that already, right? So we see that that's going to have a massive growth as well with a CAGR of 18%, which is starting from a high base. So that is once again actually pretty high, right? And I'm not sure about you, but when I look at my sort of usage patterns, I would rather use AI that is integrated into an application than to go to an AI tool. It just makes more sense, right? Because that tool that we're using is there for a purpose, and AI is helping to make it a little bit more user-friendly, a bit more efficient for you to use. So we see that the second category there, the indirect AI traffic, will have a huge impact on networks. So anyway, look, I'm sure you knew most of that already, but that was just to put things into perspective. And I wanted to get into the internals of AI, right? How AI works and all that. So at a very basic level, there are a number of different phases as part of developing AI models and using them. The first phase is what we call pre-training, right? So pre-training is basically where you're training a model based on a really, really large data set. So lots of information, like ChatGPT was fed entire contents of books, encyclopedias, and many other sources of information. So bulk data that is used in order to train a model. Given that it was a LLM, a language model, it was about learning about relationships between words and grammar, syntax, being able to predict text, right? So by detecting patterns in it. The second phase is fine tuning. So the first phase is more general. fine tuning is really taking that model that we get and training it better, fine tuning it for a very specific application. So I'll look at a few of these applications, and inference is really the application side of it, right? So you've got a model. Now you've got to use that model to solve problems. So we input problems. It could be about summarizing text. It could be about generating new images and so on. But it's producing original new content. So the three different phases, and they all have different impacts on the network. So very quickly, in an illustrative sort of way, looking at the life of a large language model, right? So we started with an initial data set, like I said, GPT-3. If you look at that, so only a few years ago, it had a data set of 570 gigabytes, right? Quite large. Llama 2, 10 terabytes. GPT-4, by all accounts, had an insane data set, almost a petabyte of information. So that's almost 2,000 times as much as ChatGPT or GPT-3. And so then we spend millions of GPU hours taking this data and pre-training the model, right? Now, some of the key things here is the number of parameters that are associated with the model. So GPT-3, 175 billion. GPT-4, which came out at the end of 2023, or around, actually early part of 2023. And it had 1.7 trillion parameters. So an order of magnitude increase in number of parameters. What we understand is that it took about 100 days to train GPT-4, right? Using about 25,000 NVIDIA A100 GPUs. So once again, an insane amount of GPU capacity to train the model. So what comes out of that, as I said, is a foundational model, right? It's a general model. It's trained in a specific function, in this case, a language, to recognize the language, to recognize sentiment, emotion, many elements of the language. We do fine tuning, right, for a specific application. So for example, we could take that and create a chatbot out of it. For us, for example, one of the things that we're doing is we're feeding it our documentation set, and now it can be used to answer specific questions about configuring our systems. So a more directed, targeted application for that, right? And it comes out with what they call an assistant model. That model is then deployed out there. So the output of the training is a model that is then deployed out there to inference centers. And the idea of that is, as I said, to apply that, right? To solve your problems out in the market. This model is tuned over time. So as we get new data points out of the inference process that is fed back, the model is iterated and it gets better and better over time, right? So that's in brief the life of a large language model. Okay, so what's that got to do with networking? It's got a lot to do with networking, right? And one of the things that we have to really appreciate here is the difference in the requirements between the training phase and the inference phase. So if you look at the left there, the training model is one of distributed communication, right? So you've got all these GPUs, they're talking together with each other. There's a thing called collective communications that is happening between them in order to really develop the foundational model, right? And it goes through many iterations, it refines its parameters and so on. The objective is to train it as fast as possible. There's a trade-off, right? If you don't spend enough time training it, it's not going to be as accurate. If you want it to be really, really accurate, you're going to be spending a lot of time. So it's a bit of a trade-off in terms of how you do it. From a networking perspective, this is a phase that needs very high bandwidth between the GPUs, right? The node-to-node bandwidth requirement is very high. There's a lot of external storage required. Like, I spoke about terabytes. It could be petabytes, right? Going into the future as well. But it's not a real-time thing in the sense that you're not responding to user queries, right? So it's kind of done in an offline fashion in the backend. Inference, on the other hand, is really about utilizing the model. So the key parameters when it comes to inference are latency. It's going to be done as quickly as possible, and It's about how many tokens you can deliver, right? So a very important parameter here is tokens per second. How quickly we can get that out to the users. It's an online thing. People are waiting for it. So the requirements, once again, are quite different. Okay, so AI and networking. I'll spend a little bit of time talking about this. And speaking of time, I'll do a time check as well. Okay, so from the perspective of AI and networking, one of the things we've got to understand is, what do we mean when we say AI and networking, right? I mean, there are many different ways of looking at this. And as I put it there, it could be in the network, it could be over the network, it could be using the network, or it can be for the network. And I'll quickly explain what I mean by that. So first, what you see in the top left there is within the network, where we see AI functions starting to replace whatever functions have been used natively for a particular bit of processing. Now, one of the applications of that is coming about in 6G. So in 6G, for example, the radio access network will have a lot of AI and machine learning. So what were traditionally more algorithmic kind of processes are being replaced by machine learning, right? So this is where AI is replacing the actual workings of elements in our networks. The second one on the top right is your over-the-top applications. I think everyone knows that, right? So these are, I guess all your AI services like ChatGPT and so on that are running over the network. And in most cases, we as network operators are oblivious to it, right? It's just another over-the-top application. And then bottom left, you've got using networks, right? So this is a very interesting development happening where we're building networks to be treated as code, so that AI applications can consume capabilities of the network, right? So they determine that there is something required in the network in order to suit the application, they push it down through the APIs and so on. So that's using networks. And the final one is for networks, and I think that's really important. It's how you can use AI in your networks to help your operations. So AI as an assistant for operating your networks. So many different ways of doing this, right? Or many ways of utilizing AI. What I did want to delve into a little bit here is the infrastructure that is required for a generative AI build out, right? And what that actually entails. So for a large language model, we look at different parts of the network and how they impacted in terms of capacity, in terms of latency, the throughput requirements, and so on. So what I've got here is a sort of generalized end-to-end network. If we start from the right-hand side, I should have got a pointer, but anyway, so you see that dark box with AI in there. That's a single AI data center, right? Now, within this data center, you've got a data center fabric. That fabric would be used for things like training, for inferencing, and so on. And that data center is, in this example, a central data center, right? It could be owned by a hyperscaler. It could be owned by an enterprise, right? But it's a data center. We're using training and inference. Within the fabric for that, which we call the backend network, which I'll come to a little bit later, what you need is very high bandwidth connectivity between the GPUs, the inter-GPU communication, very low latency, and it's got to be pretty much lossless, right? The transfers have to be lossless. Otherwise, it has an impact on how long it takes. And we saw that is a key parameter for building foundational models, right? Is how long it takes to train it. And the traffic is elastic. When you get to the inferencing phase, it's more symmetrical in terms of traffic exchange, right? There isn't that much disparity between what is coming in and coming out. Now, the challenge with building data centers for training is that typically we find that for the large models, you cannot do everything within a single data center. The amount of compute power required and means that you have to spill across multiple data centers. So what I've got there is multiple data centers working cooperatively to develop a foundational model or training that AI data. So that brings a second requirement in, right? Now you've got to interconnect up these data centers, and they have the same requirements. You need high bandwidth, low latency, very low loss. It brings in other requirements like security, because now you're sending the data out into the wide area network. My colleague Kashimura-san will be talking a little bit about how we secure that, right? So we've done some work with some GPU as a service providers around the globe, and that's been a key requirement. That traffic, because it's sharing data that could be proprietary data, sensitive data, has to be secured. So that's what you need in that part of the network. Now, for the purpose of inferencing, as you'll see in the next slide as well, we're seeing that a lot of inferencing workloads are being pushed closer to the end users. So what I have here is an edge data center, right? It could be an edge, a telco edge. It could be an on-prem data center for an enterprise. No, it's serving the purpose of inferencing. Now, pushing it closer to the end users means that you're going to solve that problem of latency, right? Like we said, you've got to respond really, really quickly. But then that needs to be connected to the central data center, right? And what do we need here? We need high bandwidth, because you'll be pushing down new models as they get ready, right? They'll have to be deployed out to the inferencing centers. And then the final part is the user access to the inferencing network. That is not as bandwidth intensive, depending on the application. If it's text, it's not. If it's media, it may be bandwidth intensive. The flows tend to be more symmetrical, but latency is of paramount importance, right? So you see that there's a lot of thinking that needs to go into constructing the infrastructure for an AI, inferencing and training framework. I'll go through this quickly because I've kind of already sort of hinted at this. AI workloads, right, are following a typical split compute model, right? So it's not that all AI processing will be done in the cloud. There's a cooperative kind of way of doing this. There's AI assist on devices. There's AI on-prem servers, on edge servers, and the central cloud. Depending on the application, you could use any of these. In fact, you could use all of those, right, to satisfy the needs of the application. So we see that one emerging need here is to actually push that out closer to the users, as I said. And it's being driven by the latency requirement, as I said, the capacity requirement as well. The closer it is to the end users, the less capacity you have to carry in the core of the network. So as part of the work that Bell Labs Consulting did on traffic patterns, one of the interesting observations was that the growth in traffic here for AI networks is actually quite interesting. They forecast that there'll be more moderate growth in the central data centers, but a lot of the growth will be in this part of the network, right? The edge and the on-prem side of things. So a lot of the traffic will be pushed closer to the end users. So that's something we have to keep in mind as we build our edge and access networks, right? Okay, so I'm just going a little bit deeper with every slide to show you what this looks like. It looks a bit scary, but it's not. It's really repeating some stuff. But just to go into a little bit more detail, the next layer down in terms of what this looks like. What I've got at the top there is infrastructure for AI inferencing and training, right? So you see we've got the backend network. Like I said, this is the network that interconnects the GPUs and connects the GPUs to the storage and so on. And what you have is dedicated storage for all your proprietary, potentially proprietary AI data. And you've got GPU clusters, the backend network connects them. What you've got down at the bottom there is a shared infrastructure, right? So this is the front end network. This is the network where you would have your typical HPC, your compute kind of a network. But from an AI perspective, this is a network that provides access to the GPU cloud, right, to external networks. So in the front end network, you would have GPU clusters, you have CPU clusters, you have shared storage as well. So this is your more typical data center fabric that we're all familiar with. So it's a combination of these that go into building AI infrastructure. So the next layer of detail. I'll stop at some point, guys. It's not gonna, otherwise we'll just get all lost here. So looking at this in slightly more detail, right? So I spoke about the two different types of networks. The ones that have GPU clusters or solely have GPU clusters, the backend network. with dedicated storage. So you can see that that's the network that I have down there. So you've got your dedicated storage nodes, your GPU nodes, right? That's your entire training cluster. And then that connects to the front-end network. So the front-end network, your more typical leaf spine architecture with CPU or with CPU-based servers and shared storage clusters as well. The difference in capacity is actually quite large. So just from a capacity perspective, there are other major differences that I'll talk about. But just from the perspective of capacity, that backend network is where you're looking at N by 100 gig connectivity, right? Of the different systems. Whereas in a typical front end, it's more like N by 10 gig, maybe 100 gig, right? Depending on what you're doing. But there is an almost multifold difference between the capacities that you are dealing with there. So it needs different architectures. So we end up with four different kind of functions that you need when setting up an AI data center infrastructure. So firstly, as I said, the backend network. I think you've all got the idea, right? It's to connect up the GPUs. Now, one of the things I must mention here is that there's a lot of backend networks out there that are currently using InfiniBand as a protocol, right? InfiniBand has been around for more than 20 years, right? And it's being used for HPC kind of workloads and networking for that. It's a good protocol, right? It supports high speed, it's low latency, it's lossless, but there are some challenges, right? The challenges being that it's pretty much a proprietary protocol. You have to license it from NVIDIA. It limits the implementations out there. So there's been a lot of work, and I'll touch on that in a bit more detail in a few more slides, around moving to an Ethernet-based infrastructure, right? So you'll see that they are now emerging where the backend network is actually built on Ethernet. But Ethernet by itself doesn't work. And it's a bit of tuning. I'll go into that in a bit more detail. You've got your storage network, not that different, right? It's really about connecting the storage to the GPUs so that you have the data set that is used to build the model. You have your front-end network. Once again, I think this would be familiar to everyone. This is a typical leaf spine architecture running, maybe a BGP underlay EVPN or VXLAN overlay as well. And they've got an out-of-band management network to manage all of that, right? So this is not as simple as it looks, right? There's a lot involved in setting up this infrastructure. And as a result, what we're seeing out there is that there's quite a number of GPU as a service providers emerging, because not everyone can afford to invest in this. Enterprises can definitely not afford to invest in infrastructure like this. So there's a huge market coming up for GPU as a service. And in the end-to-end community, I guess this is an opportunity for the end-to-ends to set up your own GPU as a service infrastructure for the entities that you actually serve. Right. So going back to Ethernet, right? Like I mentioned, we're looking at coming up with a solution where we can use a more traditional Ethernet architecture for your backend networks. Now, the implementations that we have thus far are more around augmenting Ethernet with things like priority-based flow control, PFC, load balancing, explicit congestion notification, and so on, to really, in a way, match the capabilities of InfiniBand. Right, so that's one way of doing it, and that does work, right? We've got solutions for that as well. But what we felt was that it would actually make more sense if we built a wider set of capabilities into Ethernet, so that you could have a really viable alternative that is at least equivalent to InfiniBand, but in fact even better in terms of what it delivers. So that work was started by the group of people right at the top there, and it's a consortium called the Ultra Ethernet Consortium, UEC. Nokia are a contributor to that as well. So we're doing a few things as part of that, right? So firstly, one of the questions that we often get asked is this Ethernet? Yeah, it's absolutely Ethernet. It'll be able to run on infrastructure that supports today's Ethernet, but it's got more, right? but doesn't change the frame structure of basic Ethernet and so on. So you'll be able to run mixed workloads on the same links, for example. But it brings in a few interesting things, right? It brings in congestion control, like I said, right? Very important in order to have that lossless kind of forwarding. Security built into it. It's a first-class citizen. It's not something we're bolting on, right? As we normally do with a lot of things out there. It's got a new DMA protocol, right? So DMA, or direct memory access, is a huge part of InfiniBand, right? It's about having direct GPU to GPU transfers without involving the CPU, right? So very important. It's got instrumentation performance built into it, right? So we can actually get some really good stats and information about how it's working. So this work is well on its way. There was an expectation that the first release, UEC 1.0, would come out end of last year. We kind of missed the target, but it's imminent. So it should be coming out very, very soon, UEC 1.0. So keep your eye out for that. Okay, so I hope that's given you some idea of the the implications of AI on the infrastructure. So in the last few minutes, I'd like to tell you a little bit about what we at Nokia are doing in this space. So these, what we want to achieve as a long-term goal is really augmenting our networks, right? So at high level, we want to build networks that sense, as in when we say sense, we mean they're able to really have the finger on the pulse, you could say, right? Be getting a constant stream of information from the network, telemetry information, streaming telemetry information from the network, so that it kind of knows what's going on. We want it to think, right? So with the help of AI and that deluge of information that we are now getting from the network, to actually make sense of it. Now, what is actually going on in the network? What should I pay attention to? Am I about to break something? Is a baseline being breached, for example? So this is where AI comes in, right? To be able to help to take on that mass data and come out with some conclusions that help you with managing network. And then the final element is to act, right? To take whatever comes out of it and act on it. So implement it in the network to resolve the issue, or to address capacity management issues, or whatever you've concluded, implement it in the network. And then you do the whole process again, right? So this is a whole closed loop automation framework that we've been aiming for a very, very long time. And we strongly believe that AI can play a really strong part in this. The other area is actually something that is a bit more, I guess, immediate, is about using generative AI. And I alluded to an example earlier on about us feeding our documentations into a LLM model, a Gen AI model that we can then use, or that our users can use in order to manage their networks, right? So it's one thing to understand how boxes are configured and so on, but if you can pair that with the actual state of the network, right? So the LLMs is not just or the model is not just taking in and understanding the syntax, the structure, how you configure it, but has also got an almost real-time awareness of the state of your network. Then you can take those two bits of information and really do some smart things with it, right? So it allows network operators to interact with your network system, such as your routers or your management system, in natural language, and say, hey, how do I configure a BGP peer to X? And it spits out the config. Or it can say, hey, what is the reason? What is the root? Give me a root cause analysis for why my service is down, and it can look at all the statistical data, the configuration, and so on, and tell you what's going on. So it's this is something that can really elevate the operational experience for a lot of our network operators. So at Nokia, we when it comes to the data center, there's a number of different areas where we have solutions. I wanted to quickly go through those for you. The data center fabric, right? We've got solutions around the entire data center fabric. I'll spend a bit more time talking about this. to highlight, some of the key differentiators we bring to the market. We've got data center gateway solutions as well. Now, data center gateway is actually very interesting, right? The data center fabric tends to be relatively simple. We have very homogeneous kind of architectures. It's really about speeds and feeds, and it doesn't need any complicated things. You can use unbuffered systems and so on. Whereas the data center gateways are more interesting because they are straddling two domains, right? On one side you've got your data center fabric. On the other side, you've got a wide area network. So they've got to work between the two domains. So that gets a bit more complicated. So we've got great solutions for that. Data center interconnect, we've got solutions at both the IP and optical layer for interconnecting data centers. You saw how important that was, right? With the collaborative work that is done for AI training across multiple data centers. Automation, very, very important. I'll touch a bit more on automation. And finally, security, right? So two elements of security that Kashimura-san will be talking about around DDoS using our deep field system. And more recently, there's a lot of work that is being happening on making network communications quantum safe, right? So once again, Kashimura-san will go into a bit more detail. We've got some solutions around that as well. So the fabric that we have has three essential components, right? So starting from the bottom there, we've got the hardware, right? So we've got a complete set of platforms. I'll go into that in a bit more detail. They've been designed for very high performance, energy efficiency, and with the right feature set. Running on these platforms is what we call SR Linux. That is our next generation network operating system that we built from the ground up, but we used Linux as a foundation. So for those of you who've worked with Nokia equipment, you'll know that we are a very strong player in the wide area network space in terms of routers, number one in North America, number one in edge globally, and so on. So what we did was we took the code base, a lot of the great work we've done in that operating system, the SR operating system, and ported it to SR Linux. SR Linux is a very conscious choice. We wanted to come up with a system that is open, that is extensible, as modular, all right? So we built it on top of SR Linux, on top of Linux. And then on top of that, we've got a brand new automation system. We're calling it event-driven automation, or EDA. And I'll go into a bit more detail about that. It's all about having a system that is fast, that's simple, and is reliable. So, okay, in terms of the fabric solution, I will not spend too much time on this, but we've got it all covered. Front-end network, back-end network. We've got non-blocking fabrics, whether you're running IP, whether you're running EVPN, it's supported. It is based on merchant silicon, right? So very, very cost-optimized platforms. Depending on what you're using, we've got solutions that are buffered. We've got solutions that are unbuffered as well. We've got solutions for the out of band as well. So if you look at the four types of networks that I alluded to earlier, your front end network, your back end network, your management network, and so on, we've got solutions for all of them, right? This is what it looks like. Talk to us if you want to know more details about this, but we've got leaf platforms, spine, super spine, and so on, right? There's a couple of things I just want to state here. If you look at these large platforms on the right, you think, hey, hang on, this is unusual. We don't see this in the data center. It's got slightly more limited application, but it does have applications for the larger workloads. So the 7250 IXR 6E and 10E were developed specifically for a US hyperscaler, right? So they had very specific requirements about what they wanted. We built a platform for them. The more interesting one also is that last platform. That's a very tall platform. It looks like two platforms sitting on top of each other. But believe me, it's a single box. It takes up a whole rack. And it's not the sort of thing we normally would develop. But another hyperscaler, not the one that we built the 6E and 10E for, came to us and said, hey, we have a requirement for a platform like this. So we actually shipped the first two of these the week before last, right? It's a massive system. It's got 576 ports of 800 gig at line rate. So if you do the math, it's just under half a petabit per second. So not one, the largest system we've ever developed. So yeah, it's in the data center fabric space. You've got to be able to scale from the smallest platforms, management platforms, down or up to the half petabit kind of systems. And we continue to invest in that market to make sure that we've got your needs covered. So the last area I wanted to touch on is EDA, right? The event-driven automation. When we set out to this to build a system, we had a very very simple objective, and that was to drive errors down to zero. So to allow you to build a network that could approach zero downtime, right? How do you do this? How do you build a network that is almost zero downtime? We feel automation is the key. And in fact, I'll tell you a it's not quite a story, but I was having a conversation with the CTO for an Asia Pacific operator a few months ago, and we were talking about things like stability and resiliency. And he made a statement that I don't think I'll ever forget. It's not super insightful, but it kind of stuck in my head, right? Because it's simple and it makes sense. He said, it's remarkable how stable the network is when no one is touching it. And it's okay, we know that, right? But it's when you say that, what do you mean when no one is touching it? When no human is touching it, right? So if we can automate it, I think we can go a long way towards making networks a lot simpler. So we set out, whoops, what happened there? Did it? So we set out to build just that, right? So what we did is we came up with the idea of event-driven automation, a system that is built to react to events that are happening in your network. And instead of starting from scratch, we said, okay, let's use something that's actually known to the market, which is Kubernetes, right? We're the most, I guess, famous orchestration system for containerized applications. We took that and we enhanced it to do the same thing for networks. If you could orchestrate containerized applications, maybe you could orchestrate networks as well. And that's what we've done. We've built on top of Kubernetes, and it's delivering those three things that we said, right? Reliable operations. So completely intent-driven, single source of truth. You configure the system, or you tell the system what it should be. It then pushes it out to the rest of the network, and you can be assured that it's done, right? It's got the reliability built into it, so it either does everything or it does nothing, right? So you have complete feedback from the network as to whether your intents have been implemented into the network, and you don't have to do it on a node by node basis. It gets done on the network as a whole. It simplifies lifecycle management, right? So it's done. No, the idea was that we, like I said, we want to drive downtime to zero. So it's used for day zero stuff, for designing the network. It's got a digital twin capability. Day one for deploying it out in the network, and very importantly for day 2+ kind of operations, right? To make sure that it continues to run, matches the configuration, and so on. It's vendor agnostic, by the way. So this is not restricted to just Nokia switches, right? No Nokia hardware. It works in a vendor agnostic manner. So the three elements of it I've already talked about, so I'll just skip through this really quickly. Of the data center fabric solution we have is about reliable networking, right? One of the sort of mantras that we have is, the network should just work. You should not be really concerned about the network. This is one part of the network that should work. Like in an end-to-end environment, I really liked the pyramid that David Wiles put up yesterday, right? At the top of it were the researchers, right? You don't want them worrying about the network, unless they are researching on the network, of course, right? Then they'll be interested in it. But otherwise, you just want to provide them a network that just works. And that is really key. The second area is around enhancing the operations, right? It has to be, you've got to be able to trust that automation, right? I mean, so the thing about automation is, when we talk to people, it's like, yeah, I don't want to take my hand off the steering wheel. I'm just worried, right? It's not going to work. So you've got to have that. that reliability so that you can actually, take your foot off the pedal and your hands off the steering wheel. And it's got to be able to be integrated into your systems. And using things like Kubernetes, like Linux, is like I said, a very conscious choice. So it's a lot more easier to operationalize into your network. I'm kind of running out of time, but I'll just flesh up this case study. So this is a university in North America where we've deployed our data center fabric solution. So they were looking at building a sort of a shared sort of cluster which was doing high performance compute as well as AI. So what you see here is, you probably can't read that, but a cluster of CPU nodes and a smaller cluster of GPU nodes. You've got a storage cluster as well. And they're building it on the Nokia data center fabric infrastructure. You've got the 7250 IXR-H4 switches and so on in that part of the network. Very high speed interconnects, right? 400 gig interconnects between these devices and so on. So yeah, we're already seeing applications for this in research and education institutes. Okay, so that brings me to the end of the presentation. What I want to leave you with is that there are many aspects to building infrastructure for AI networks, right? And that depends on what you're doing. Is it AI on the network, in the network, over the network, for the network, and so on. At Nokia, we approaching it from the angle of expertise, great expertise in IP routing solutions, right? Which we've been doing for 25 years now, and we're bringing that technology now to the data center fabric. We're covering the connectivity angle with a broad range of hardware platforms. Automation to us is a first-class citizen as well, right? As we said, it's the idea, the thing that we're working towards is that it should just work, right? It should work all the time. And it's got to be done in a very secure fashion, right? And I think that's a good segue for me to wrap up, because Kashimura-san will be picking up that angle of security and talking about this over the next few minutes. So thank you very much. Do we have time for questions?
Thank you, Paresh. Very insightful presentation, and it looks like we need it all, right? Very high bandwidth, very low latency, high flexibility, right? Actually, a few presenters in the sessions this week have been talking about distributed quantum computing, right? And when you get distribution, right? So of course, communication is very important. And so this perhaps as a segue. So then if it's distributed, right, we have so many elements. Kashimura-san, how do we secure it? What can we do, right? What are the countermeasures that we have? Please.
Okay, hello, good morning, everyone. I'm Yasu Kashimura from Nokia. For today, I will be talking about the security aspect, how we can protect the network from the many of the threats in the world. So let me start with my introduction. I started my career at NTT and as a network engineer, and worked for the Cisco systems many years, and moved to Alcatel-Lucent as a consulting engineer. And after the acquisition by Nokia of the Alcatel-Lucent, now that I'm leading the IP product team in Japan. So when we talk about the DDoS, it is a really common security threat for your network as well. And you may be wondering why the Nokia is talking about DDoS. Many of you know that the Nokia as a mobile handset vendor many years. But now that we move to the end-to-end network solution provider, with including radio access and also IP transport, WDM transport, and also a cloud and packet core and things. So we are providing an end-to-end solution as a network equipment vendors, solution vendors. And we acquired one startup company called Deepfield. That company has developing the solution for the network traffic analytics and also a security DDoS detection. Now that is part of our solution, with combining with other IP router and related solutions as well. And the deepfield is doing the traffic analytics based on the gathered information from our friendly customer, contracted customer in the worldwide. And we are making the threat report, Nokia threat intelligence report every year, based on that year's analytics and the traffic analytics, DDoS threat analytics. That is kind of the detailed security report we are publishing every year. I think this material will be distributed to you after the event, and we put the link. And you can see that much more detailed information on the report. But for today, let me introduce some findings in the last year. What happened in the world in the DDoS aspect? So when we see some history of the DDoS situation, until the 2020, most of the traffic from the DDoS is about the spoofed traffic, like using a DDoS, a DNS, or NTP, and cache. Such kind of spoofed traffic is a major attacks in the world. And after the 2020, along with the increased high number of the IoT devices in the internet, botnet DDoS traffic is also dramatically increased. Many of the IoT devices, non-human operated devices, not like a PC or the mobile phone, the smart home, many of the devices are connected to the internet. And along with that, we see that a lot of threat is increased for those kind of many types of the hosts. And in 2025, we started seeing a lot of the cases the hacker is leveraging the AI for attacking. The more faster the target rotation or the list out the potential threat in the world, they started using the AI to list out the target. And the DDoS traffic keep growing. To compare with the 2023, the 24, in 1 year, we see that DDoS traffic increase about 166%. So it's really big growth, and it's keep growing. And attack frequency is also increasing. In 2 years ago, we see that attack event is 1 or 2 times per day, but now it's more than 100 times per day. That kind of the frequency is also increasing. And when we see the geopolitical situation, when we see the total number of the percentage of the DDoS event, when we include the Asia and Oceania APAC area, it sees that about 25% of the attack is happening in the APAC area. And the attack vector is also changing. As I mentioned, before the spoofed traffic like a DNS amplification is a major attack. It's still major, but the total percentage is decreasing. Besides the botnet or the quick type of the attack vector is also increasing in the recent years. And also other vectors is decreasing, like NTP or CLDAP, the memcache. That kind of the attack vector is decreasing. With including the spoofed traffic and UDP flooding, such kind of simple attack vectors also include the DNS, botnet, quick, this kind of traffic. The total number percentage is about 95%. Besides, the application layer traffic is decreasing, less than maybe 5% or so. And botnet, we see that many of the cases for the botnet is sending a lot of huge amount of the DDoS traffic. And one issue we see on the botnet is that the attack traffic is not spoof traffic. That is sent out from the normal or the usual the host. It's really hard to detect this traffic is the bad or good from the standard host. And each of the traffic flow from the botnet is not so huge. The traffic rate is very tiny, but it's sent out from the thousands of the host, botnet host. As a total, we see a lot of the traffic, huge traffic amount. So due to the low bandwidth of each of the DDoS flow, it's really hard to detect the DDoS traffic in the normal, traditional detection way. For example, one of our customer in NEPAC see that they are providing the FTTH service for the parking meter. The car parking company is providing the parking meter in the street. And thousands of the parking meter host is infected and becoming a botnet. And that thousands of the parking meters started sending out a huge traffic to the internet. So many of the infected case we started seeing for the botnet area. And also another case we started seeing from last year is using the residential proxy. The residential proxy application is known as for the security for the user purpose. User want to hide their IP address from the outside or the internet side. So they using some kind of application called the residential proxy. And it's provided for your PC or we can use it on the mobile phone as well, smartphone as well. And that kind of application is misused or badly used by hackers, and it's act as a DDoS senders in the internet. And the number of the sources or the number of the victims, mean the target IP address, is also we see the high number of the IP addresses. So carpet bombing attack is also we see in a lot, and 13% of the carpet bombing attacks is targeting the more than 256 destination address. And also in the more larger cases, we see the attacks are targeted more than 1,000 hosts, 1,000 IP addresses. In the largest case, we see the more than 16,000 target IP address is attacked. So we showed some real example from our customer for the attack example. Sample one shows that many of the source IP address is sending a very huge traffic, huge high rate of the traffic. And also sample two shows that many of the source IP, but the traffic rate is not so high. Sample three is the combination of the one and two. We see a lot of the source and destination IP address, and the traffic volume is also huge. So we see the many cases of the traffic, DDoS traffic is sent out from the huge number of the source IP, and also target is also huge number of the destination IP. And also duration of the attack is also becoming shorter and shorter. 44% of the DDoS traffic is finished less than 5 minutes, meaning that we need more faster detection and mitigation to protect from those kind of the short duration DDoS attacks. And in this example, in the left-hand side, you can see the many of the red peak. It shows that attacker is changing the attack vectors, like a source address, destination address, or the kind of attack vectors every 10 seconds. It's really hard to track, and it's really difficult to mitigate. So as I shown some example of what we are finding, the one was growing. We see a lot of the botnet and residential proxy, new type of the attack sources. And attack duration is becoming shorter. We need a more faster detection. This kind of the attack situation is dramatically changing in the recent years. And as we've seen the many of the news, many of the organization, enterprise, CSP, many of the customers are attacked from the hackers. So we need to be care. We need to prepare how we can protect the network. So how we are observing this kind of the data from the internet. So we are gathering the information from the worldwide internet area, like botnets, where we can have we are seeing the botnets host and DDoS amplifier sources exist, and those the connected hosts in the internet have like a security vulnerabilities, CVEs, any of the threat, and IP booters, and vulnerable hosts. This kind of the data we are gathering from the internet. Then how? So we are putting some kind of a crawling agent on the cloud, and that agent is checking crawling every single accessible IP address in the internet, IPv4 and IPv6 address internet. And we are getting the data, this IP address is used for what, and this address has, this host has any kind of security threat or not. This kind of the information we are gathering from the internet by crawling. And based on that data, DDoS vectors and botnets information and the known reflectors, those kind of security information that we are building as a security-related database. It's called a secure genome. It is our center of the database. That we are gathering those data, and also we see that a lot of the new attack types or the attack way. For those data, that we are gathering some of the customers for the voluntary based. That we have some friendly customers, voluntary customers are providing the real attack data to our database. And our database is running such kind of attack data in the worldwide, happening in the worldwide. And in the machine learning AI based, we are running the new type of any kind of the attack vectors, vulnerabilities, the new way of attack. Based on that, we are making the more better understanding of the security threat in the existing in the world. So then how we can defend our network from that kind of DDoS. So as I mentioned, we need a more granular and faster way of the detection and mitigation to protect against those type of the changing DDoS types. And what we are providing as a solution, it's called a Deep Field Defender. It's kind of the flow collector-based mitigation system. And from the IP network side, the flow information, like a net flow, S flow, we are gathering the flow-based information. And based on that data, we will analyze what DDoS is happening in the customer's network. And to analyze that data, we are doing a multiple dimensional analytics. Basically, we use that flow data, and also, as I mentioned, our security-related database, Secure Genome, is used. What kind of the DDoS flow is happening on the customer network. Then after we analyze and detect the DDoS traffic, we will have the mitigation action to the network itself. It may be flow spec, BGP flow spec, or in the more newer way, latest way is that the program the filters on the routers or any kind of devices to filter out the DDoS traffic. So our good things on the deep field is that we are not detecting the DDoS traffic based on the threshold. The more traditional way, traditional DDoS detection uses the threshold to detect the DDoS traffic. It means that very narrow band-wise DDoS traffic cannot be detected. But in our deep field, it started the traffic analysis solution. what kind of application is flowing in the network. That is our original solution. And after the result of the more detailed analytics of the flow, we could see the bad traffic as a result of the detailed analytics. We are recognizing the DDoS traffic as one of the application flow, not the threshold based. So even if you use that our solution for the DDoS detection, you don't need to configure any kind of threshold for the detection. It's automatically detect the DDoS traffic as one of the application flow kind of things. Then to protect the network, as I mentioned, flow spec is a very standard way that we can work with, interact with any kind of routers for the program the filters. But filters can be programmed on the with using the BGP flow spec. It's a very simple. It's a very just a 5-tuple based ACL can be configured. But to protect from the very complicated traffic, DDoS traffic, that we need a more deeper level of the ACL, not only for the destination, source IP, protocol, port numbers, but also we also need to program the packet lengths or the TCP flags or the TTL to protect that, to filter out the DDoS traffic. We need a more detailed way. To program that such kind of the more detailed, deeper level of the ACL to filter out the DDoS traffic, that we use the NetFlow to program the detailed filter to the devices. And we have the mitigation, mitigation compilation engine. This is that after the detection, we automatically generate the most optimized ACL access list for the routers. In the previous example, you see that some type of the DDoS is detected, and you can see the right-hand side that you can see the circle, and it shows that 239 filters, 1,700 filters. This shows that how many lines, how many filter lines is required to filter out this DDoS traffic. So we will create this kind of the most optimized filters to be programmed to the network devices. On the network device side, it also needs good performance, even by programming the thousands of the filters on the routers. Some platform may see that some performance degradation when it programmed many of the filters. But our routers, Nokia routers, does not have such issue. Even we have the thousands of the filters with a more deeper level of the ACL, it does not affect any performance or throughput. And for the more faster detection, we have the way called sample packet mirroring. It's not a NetFlow based. We will get the sampled packet mirror packet, but not all packet. It's sample based, like a NetFlow, but we will send out the real traffic packet information to the deep field detection system. We will see that the more real-time traffic is taken from the network, that we see the more, we can do the more faster detection. In the NetFlow, the most shorter the update timing will be 30 seconds. Even any kind of attack happening, that sampled NetFlow data is coming every 30 seconds. We need to wait 30 seconds at maximum. Then the mitigation action it need to be taken. In the most best case, it takes some minutes or so. In the sample packet mirroring, we see the real-time traffic for the detection, that we can detect the DDoS traffic in seconds, then act more fast. So in this example, the detection and mitigation action can be done within 30 seconds. We can do much more faster mitigation and detection with using the sample packet mirroring. And also we have the traditional mitigation appliance as well, that we can leverage that our router processor-based platform for the mitigation. We can have the terabit class of the mitigation. We can have the 2.4 terabps mitigation performance with a combination of the router platform and also a server platform as a one appliance. Logically, it acts as a one devices. So by filtering, programming the filter on the router, not in the traditional scrubbing center based mitigation. As you know, the traditional scrubbing center solution is very expensive. Bit mitigation cost is very high. So to optimize those costs for the DDoS mitigation, that we can have the router, we can reuse the router's filter function for the first level of the mitigation, filter out most of the DDoS traffic on the router as a gateway or the edge network, edge routers, as an edge side of the your network. And also the traditional mitigation dedicated devices, also we can provide. So with using that, we can do the more network-wide DDoS mitigation, DDoS detection and mitigation. Normally we are much caring about the threat or the attack from the internet side. So DDoS detection and mitigation is mainly focusing on the internet side. But as I mentioned, we also need to be care about the botnet. Your subscribers, your hosts may be infected and becoming a hotnet. It is also a real threat you may have. So we need to have the more multi-dimensional protection, not only for the internet gateway side, and also edge or the subscriber network side as well. So one of the example, our customer reference, it is IX customer. It's not the NLAN or research networking, but it is IX customer. But they are started providing DDoS mitigation services on the routers, on the IX switches actually. On the IX's edge routers, they program the detected DDoS traffic filters on the routers and do the edge router-based mitigation. It is provided for their IX users. And this kind of the users is very increasing. And we have the national research network types of customer use case as well. There are some of the customer already deployed a deep field solution for the DDoS detection and mitigation. So as a summary, we have the more advanced way of the DDoS mitigation and detection. And we are using the ML and the AI for having more advanced database for the potential threat information in the world. And we can also provide a more faster detection and mitigation way. And also such kind of protection must be multi-angle, not only for the internet side, but also we need to care about the attacks from your user side as well. So the DDoS is one of the big topic for the network security. And as Parish mentioned in the previous session, that we are also working on the transport layer security, how we can protect the data flowing in your network from the hackers. So usually we are using the security way like IPsec, but it's said that when we have the quantum computers, current normal the encryption way can be easily decrypted. And we need a more stronger quantum safe encryption to protect our data from the threat. And we have the many dimensions of the network security that we will focus on the transport layer security. People say that enclosed network closed network is very safe, but it may not be true. Some people may sneak your data, store your data from the network by using tap or some data is sneaked from your fibers as well. So your data may be stolen. We need a more stronger encryption to protect the data. And we can provide a more stronger way of the encryption, decryption on the router equipment. Our router supports the very fast, very high bandwidth, high throughput, and low latency encryption and decryption with a 256 bytes key encryption, decryption. And in this picture, it shows that the end-to-end network architecture for the end-to-end security. And you know, the MACsec is a very standard way for encryption in the transport layer 2 area. And we can use that the MACsec in the access area. But in the backbone area, like a P2P with including backbone network, we can use that we call the AnySec. It is a new encryption tunnel way with using the MACsec encryption. You can make the overlay tunnel, overlay secure tunnel over the network. And the middle of the network, like a backbone network, backbone router, does not need to care about the encryption, decryption. P and P, those PE side need to support this encryption, decryption. But we can provide like a 400G, 800G, even such kind of a high-speed interface. We can provide a line-led encryption, decryption with a very low latency. I put some data on this data is took with using the 400G interfaces, with using the encryption, decryption. And you can see some very small difference with the no encryption or with encryption. We can provide a very low latency and high bandwidth, high throughput encryption, decryption functionality on our routers. And for the overlay tunneling, we reusing the MACsec 802.1ae headers. And on top, we can see that the MACsec, normal standard way of the MACsec encryption. And we are reusing this .1ae header to be put on any layer. It may be after the VLAN tag, .1q tag, or it may be after the MPLS label, or maybe segment routing seat. We can have the more flexibility on the placement of this .1a header. The intermediate router can treat these encrypted packet like a normal VLAN frames, or the MPLS frames, or IP packet. So with using that, we can use that more flexible secure tunnel with a very high bandwidth. Now that we are proposing this way to be a standard at the IEEE and also IETF as well. And if you are interested for a standardization, please let us know. So we also getting the certification from the NIST for the quantum safe networking, and also we also have the more secure key generation and distribution solution. But we can work with any other solution for the QKD, any kind of solution. We are really open. So this kind of the quantum safe networking is not so much common, especially in Japan market actually. But when we see that many of the customer is starting apply this kind of the quantum safe encryption, decryption way for their customers. One of the example, we see that in North America, one of the GPU as a service customer, they are providing a GPU AI platform as a service to their end users. And they are treating that the very critical information from the customers. Customer is putting many of the learning data or the land logic is also inference data. Many of the critical data, know-how data of the customers for the AI use case. To protect those critical information, they are putting this AnySec encryption as their backbone. Inter-DC connection, inter-GPU DC connection, they are providing this very strong encryption tunnel. So today I talked about two different aspects of the security. One is DDoS and one is the transport encryption, and we can combine together. So from the threat from the internet or your subscriber, your users regarding the DDoS, that we can apply the deep feed for the more network-wide protection from these types of attack traffic. And also to protect your data from your network, that we can apply this AnySec encryption, quantum safe encryption in the network layers. That we can have the multiple layers of the protection from the potential threat, potential security threat. I think not only for the CSP or the normal enterprise, this kind of NLAN, the research and educational organization also becomes a potential target of the attackers. So we need to well care about how we can protect the network from this kind of many types of threat. Okay, that's all from me. That's all end of my presentation. Thank you for